discussion part. I think we will first finish the discussion part of yesterday's talk and then proceed with the talk about solid state NMR. And in between, I have a small announcement. So Dr. Vinesh and me are planning and preparing to constitute a Kerala Magnetic Resonance Society. And this society is for exchanging or transferring knowledge about NMR spectroscopy between different institutions like that. And we will organize webinars during this time and later seminars, workshops, all kind of training programs repeatedly. That is the primary aim of this society. And I hope all of you will be interested in it and all of you will be interested to join this. So we created a Gmail, a Google email account or email address for this, and please express your interest through email to this email address. The email address is kmrs.nmr.
You can put in the chat box probably.
Yeah, at gmail.com.
Do you charge something for this, for joining this?
Yeah, this is
torque against this M0. So what you need, or what we need, is to get this M0 out of the Z plane. So this is Z plane, and you want the M0 out of the Z axis. Okay, so now before you apply a radio frequency pulse, the M0 is aligned with the B0 field. So we cannot detect M0 because it is submerged by the B0 field. M0 is very small, tiny guy compared to what is ZV. B0 field will be huge. So you cannot detect M0 in the direction of B0. So we apply a radio frequency which can be in any direction other than the Z direction, but the best torque, because it is a cross product, the physics will tell you it's a cross product. So the best torque is applied if you are degree plane. So it can be either X, Y axis or X, Y plane. Okay. So that's basic physics. So you have to apply a radio frequency in this direction. Okay, then you will have an oscillating radio frequency. It goes oscillating like that, and that is enough to get this M0 out. Okay, now the power, when I said the amplifiers, you remember the amplifier? The amplifier gives you the power. The power basically tells you how whether you will get a 90-degree pulse for a particular time or a 180-degree pulse and things like that. So power basically determines where you end up, the magnetization end up. Okay, so a 90-degree pulse would be M0 going from the Z axis to either X or Y axis. That is a 90-degree pulse. M0 going to minus Z axis. So M0 meaning from plus Z to minus Z, that will be a 180-degree pulse. The power for that would be different. Okay, or power is the time can be changed. So there are two things. Either you increase the power or increase the time in order to get a 180-degree pulse. Okay, I hope that is clear for the first question. Then come. No. There are more questions actually. So high concentration sample is okay for 37 when it comes to 1H. Most times we don't get proper spectrum for highly concentrated samples. Proper splitting of peaks is not there. Why is it so? Now, high concentration sample is okay, so he or she understands what is why we require high concentration, but we don't get proper spectrum for even highly concentrated sample. That it can be many reasons. cryogens. Now, in a high spectral broadening, he or she specifically says why splitting is not there. That means there is spectral broadening. That means the line width has increased. So, okay. Now, normally, if the line width is short, is narrow, then you can get the splitting. If the line width has increased, then you don't the splitting. Especially the small splitting, this proton-proton vicinal couplings and all, they get submerged, right? So if you need to get a proper splitting, what is on a spectrometer side, what you have to do is to have a very good shimmed magnet. That means that 5 centimeter magnet, right? Have 5 centimeter of your sample. That has to be highly homogeneous. Okay, the shimming has to be spectacular. Okay, so shimming has to be nice. Okay, that is the important thing on the spectrometer side. Now, there can be many things that is going on the other side, which is you have an inhomogeneous sample. Okay, what is an inhomogeneous sample? You expect that your solute, whatever your molecule, is fully soluble in your solvent. Now, if your solute is not soluble, then you have an inhomogeneity in the solution, right? There is a solid phase, there is a liquid phase. Okay, so that inhomogeneity can cause broadening of the peak because you have a broad signal. On top of it, you have a narrow signal from the solution state, broad signal from the solid part, and then the narrow signal from the solution part. So you get a broadening, net broadening. Okay, there can be also other possibility that there is some chemical exchange going on. Okay, if there is chemical exchange, then you will get broadening. Okay, chemical exchange can lead to broadening. For this is only 3 possible scenarios for small molecules. If you are working on polymers and all, if the size of the polymer is really huge, then there is, because a molecule is not tumbling very fast in solution. I will tell you in detail a little later in solid state NMR. If the molecules are not tumbling very fast, then your relaxation rates are pretty fast, and that will give you a very broadened line. Okay, so if you are working with large molecules, that will give you a very broadened line, even if your concentrations are really high. If you really want to get a good spectrum, then you have to go to solid state NMR. I mean, reasonable good spectrum, then you have to go to solid state NMR. So if you are still working on small molecules, then it could be chemical exchange. Chemical exchange can broaden the signal because the protons. I assume that the person is talking about hydrogen NMR. The proton has during the NMR, when you're measuring the NMR, the protons experience 2 chemical shifts. If there is an exchange going on between A giving B, so the chemical environment in A and B will be different. So during the NMR time scale, they will have different chemical shifts. So what you see is the average of this chemical shift, which leads to broadening. Okay, so that could be one of the problem that you can face. Now there are the third question. What is the need of 2 sets of cryogens in the NMR? Yeah. So you typically in your room temperature where you have AC and all, it was kept at 25 or max. Actually, it should be kept at 18 degrees Celsius. Okay. So around 270 Kelvin. 270 Kelvin is what you put. Sorry, 290 Kelvin. 290 Kelvin is what you have at room temperature. That temperature outside in the room. Now the superconducting magnet has to be at helium temperature, liquid helium temperature, which is around 4 Kelvin. Okay, there is a huge temperature gradient, 274 plus 290 to 4 Kelvin. That reduce this pressure. But if that is the case, then the heat loss or the heat will just transfer from the outside into the helium vessel. Even if you have vacuum and everything, it is possible to transfer heat, and that is possible because you see, you know that sun, the light, light of the, if we don't get energy, the heat has to be transmitted from the sun to earth, right? And in between it is space, and still heat transfers. The same way heat will transfer, even if there is vacuum, heat will transfer from outside into the helium vessel, helium temperature. So that will warm up the helium and we will quench the magnet. In order to reduce it, we put it under a liquid nitrogen basket, which is at minus 100 degrees Celsius. Okay, so that would cushion the blow from the radiation transfer. Okay, so that to reduce that is only the why we need 2 sets of cryogens. If you want, you can make a 3 set of cryogens, but then it will going to be bulky, more costly, and everything is going to get cost. So this is the minimum they will that is required, that is cost effective. Yeah, can some RF coil can be adjusted in such a way that same coil can be used for HC and other elements? Will that cause a problem of noise in the result? Yeah, so this is a good question. So an RF coil, the problem with RF coil is that RF coil is there, but then how do you tune the coil? This is an LC circuit. You probably have studied in your +2, +2 physics, LC circuit, and the resonance frequency of an LC circuit, right? 1/√2 LC, right? That was a thing. Capacitance. It has a capacitance. Now the problem with capacitance is that you cannot have a really huge capacitor that will be able to have a frequency. What we are doing in LC or whatever that is in the probe as well as in our radio is when you're tuning this knob, you're basically adjusting the capacitance. You basically adjusting the capacitance such that the tuning frequency of that LC circuit matches the frequency from the airwaves, right? So this is what we are doing when we are tuning a radio. The same thing is what is happening in NMR also. Now the problem is when we have a proton at 9.4 Tesla, that means 400 megahertz, and carbon, which is at 100 megahertz. That is a difference of by a factor of 4, right? Or 4 times higher. The carbon's frequency, proton frequency is 4 times higher than the the carbon frequency. So if you tune it, tune it to carbon, and then if you try to reach proton with the same frequency, it will not be possible. There is no capacitors that can actually do it. Okay, so if you have such a efficient capacitance, then it is possible to do it, but it is not possible. Also, we would like to detect, right? We would like to detect. We would like to detect on proton. We rather not detect on carbon because the gyromagnetic ratio of proton is higher. So you don't want that carbon pulsing together on proton and carbon will not be possible for a single coil. So if you do an HSQC, for example, it is not possible to simultaneously pulse on carbon and proton. If Professor Madhu and probably have explained to you what is an HSQC. So in that HSQC, you will have to pulse on carbon and proton simultaneously. It's called double resonance. These are old nomenclature, double resonance. You will not be able to do that if it is on the same coil. Okay, so that is not possible. So so in doing all of this, that we have these 2 different coils. First important thing is the whole engineering problem, that is you cannot have a sufficiently large capacitor to tune C and H simultaneously. And the second thing, you will not be able to do double resonance NMR. Okay. And will that cause a problem? Since we use pulse for radio frequency to collect FID, exactly what we supply the frequency tuning? Right. So this is also a good question. Since we use a pulse for radio frequency to collect FID. Now I said, of course, probably when I said when you do a pulse, then you get a pulse is like that, right? And then if you Fourier transform the pulse, you will get something like that. So this is the frequency. Let's say this is at 400 megahertz. Then this center portion of this one would be 400 megahertz. Right. Now there is possibility that it goes this way and that way, right? This way and that way. So there is a delta nu frequency that it can also excite, right? Delta nu frequency it can also excite. So the question is, since we use pulse radio frequency to collect the FID, exactly what we supply the frequency tuning. Now we have to tune exactly to, if we are doing at 9.4 Tesla, and if you want to observe proton, we have to tune it to 400 megahertz. Okay, exactly 400 megahertz. If it even we deviate to, let's say, 400.1 megahertz, you know how much is that? That is like 10 raised to 5 hertz. That is like 10,000, 10 or 10k, 10 kilohertz. Okay, 10 kilohertz. Now, what is that 10 kilohertz? 10 kilohertz would give you so much of, you know, at 400 megahertz, what is the 1 ppm range? 1 ppm would be 400 hertz. Okay, 10 kilo. So even 4,000 hertz, 4,000 hertz would be 10 ppm. Now 10 ppm, your proton, the whole proton will be covered, right? 10 ppm, the whole of proton will be covered. Now, if you have 10 kilohertz, that means that is another 6,000 hertz onto it. It will cover up to 20 ppm, 25 ppm. It goes up to 25 ppm. So you're basically, rather than in your ppm levels, you will be here when you are exactly at 400 megahertz. If you are 400.1, you will be somewhere around 25 ppm. Okay, and there you are pulsing. Obviously, your signal to noise will be terrible. Okay, what you need to do is, when you are, that is why you need to tune exactly at that particular, especially for this high gyromagnetic ratio. You have to be, every time when you do a NMR, you have to tune and match your proton to get the maximum signal to noise. Okay, so if it is away, what happens? Your 90-degree pulse will not be at 25 ppm. Your 90-degree pulse will be that, whatever the pulse length that was calibrated. But since all your spectra are in this region, 0 to 10 ppm, that is very far away from 25 ppm. You will not have 90-degree pulse here. 90-degree pulse will give you optimal sensitivity, okay, or 30-degree in your when you're doing that. But you will not have the right sensitivity if your offset is really, really huge. This is the offset, right? It's 25 ppm. That is really, really huge. So you don't want to do that. You have to, exactly have it at the right frequency. All right, these were the questions that I think I had. If there are further questions, you let me know. Okay.
So, is there any more questions you can ask right now? If there are no questions, then we can proceed with the solid state NMR. Please. Yeah.
Okay. Yeah, so solution NMR is wonderful actually, because solution NMR, you get very sharp lines, and that is why most of organic people like it, because it is very sharp. Each environment can be easily distinguishable. So you have a reaction, you should be able to figure out if we have only the reactants or we have actually the product also. And you should, and it's also pretty intuitive to figure out the structural elements of your compound. Now, why is that? Why is it so nice for solution NMR? Because the molecule actually is in solution. That your solute is being dissolved in a solution, and this solutes in solution. This solute molecule, or the molecule of your interest, are tumbling around in your in the sample. That the molecule are tumbling around. Now, what happens if the molecules are tumbling around? Many of this anisotropic interactions. Now, there is one interaction that I have told you, and I didn't. Because I probably others have mentioned. Professor Chari, Madhu, and others might have mentioned to you about all the types of interactions that are present in NMR. The first and foremost interaction is the Zeeman interaction, which I myself had told to you about, right? But then there are other interactions, like the coupling interaction, right? The J coupling, scalar coupling. Also, there is also anisotropic interaction. These are isotropic interactions. Coupling also can be anisotropic, but these are not really, we don't really see them. But there are anisotropic interactions, and these are the dipolar couplings and the chemical shift anisotropic interactions. Now, the problem with all these interactions are that in solution, thankfully, all these interactions are averaged out. Okay, all these interactions average out in solution. Now, why is it? Because they actually tumble. What is anisotropy? That I have to tell you, right? What is isotropic? Isotropic meaning every cell, every direction, in all directions, it has the same interaction. Okay, it is like a scalar quantity. It doesn't have any directional dependence. It's like a scalar quantity, right? Now, what is anisotropy? Anisotropy is like a vector. It needs to have a direction. It is not the same. The interaction on one direction will be different from the other direction. If you are looking at a Cartesian coordinate x, y, z, the interaction, if the nuclei are interacting in x direction, it will be different from the nuclei interacting on the y direction. It will be interacting in a different way in the z direction. So this is the anisotropy. They are not same. It's not all the way same. If isotropic interaction can be represented like a sphere. It's like a sphere molecule. Because it's very fully spherical, it's fully symmetric. Every direction, it's equal, right? So it's a sphere. But an anisotropic interaction, it can be represented like a ellipsoid, like a oval-shaped thing, but spherical, but in a 3D, right? So ellipsoid, that we call the ellipsoid. Now that is the anisotropic interaction. Okay, so there are anisotropic interactions, and thankfully in solution NMR they get averaged out. So in chemical shift is anisotropic, dipolar couplings is anisotropic. Chemical shift anisotropy is averaged to the isotropic part, which is what we see in solution NMR. You see single peak, right? You don't see an orientation dependent chemical shift. You see a single peak in solution NMR, and that is because this molecule tumbles around and samples every other space. So if you integrate over the entire space, then it comes to the isotropic component, which is what we observe in solution NMR. Dipolar coupling also is anisotropic. Again, when you integrate, because it depends on the theta, the angle between the two dipoles, and the distances. So it will, we will talk about it later. And as it tumbles around, it samples all, because it goes over the theta angles, and finally it also ends up going to zero. It actually ends up zero. So you don't see dipolar coupling in solution NMR unless you actually reintroduce them using specific alignment media. The reason why we reintroduce them is because it's very it's actually quite a good structural tool in order to understand the angle between two bonds or the distance between two bonds, and also the shape of the molecule, etc., can be figured out using the dipolar coupling. Anyway, but these informations are lost in solution NMR. But the trade-off is that you will get a very good sharp signal. Okay. Otherwise, what happens if you have a small molecule but sufficiently complicated splitting? You will break your head understanding what is the splitting. Then you have to go to the 2D NMR, 3D NMR, and all to figure out what the splitting exactly is. Right. So that is because there are a lot of splitting in it. Now, if you have dipolar couplings onto it, dipolar couplings will split exactly like J coupling. It is going to split your resonances. If you have so many splitting, because it will split with everything. It is not through space. It is not through bond. It is actually through space. Dipolar couplings is through space and not through bond. You observe dipolar coupling indirectly when you do a no-C NMR. No-C NMR in solution state, you will get information from dipolar coupling, but only the distance information. Okay, so I hope you guys studied no-C because that is a very important structural tool for determining structures of molecules. Right. So so in solution NMR, what happens is there is a rapid tumbling of molecules, averaging of anisotropic interactions, and finally you get very nice spectrum, right? These nice splitting is because of the J coupling, not the dipolar coupling, right? So what happens in solid state NMR? Now this is solution NMR of the same molecule, very sharp signal. In solid state NMR, look at the breadth. It's a static solid state NMR, strong peak broadening. Okay, strong peak broadening. To figure out what exactly is happening around in this molecule is very, very difficult, right? So you need a much more analysis that is required in solid state NMR, or even much more important techniques. So how do we get high resolution? When people say long time in solution NMR, there was NMR. Then they became high resolution NMR. What is high resolution NMR? You can individually, the resolution of the NMR has been increased through 2D, having higher magnetic field and things like that. Now, in solid state, how are we going to do? We use cross-polarization. We use 2D experiments. Then, of course, magic angle spinning. Okay, so these are the important things that we use. First, we talk about magic angle spinning. Now, why do we actually bother to study solid state NMR? There are, of course, other techniques that is very much easier to do. That is crystallography. You can do diffraction methods and study structures. Right now, that will give you this part: rigid solids, very ordered structures. If you have very ordered structures, don't do solid state NMR. It is actually pretty much easy to do X-ray crystallography, right, and get structures out of it. Now, but if the order is not met, long order, so the crystals, single, they have to be repetitive units are missing. Then if you have amorphous solids, you have soft solids, gels and all, then we can do solid state NMR, where we basically, as an NMR, the principle of NMR is the same, that we actually look at the local environment. Changes in the local environment will be reflected in the peaks, right? And if you are looking at that, then if you are actually monitoring that, these can be used. Soft solids can be used, amorphous solids can be used. Yeah. The only difference, of course, is that extracting the information can be quite tedious. Well, extracting this information, it is not as straightforward as, and it's also not as straightforward doing. The measuring is also not that straightforward, like the solution NMR. The electronics are also quite different from the solution NMR. I mean, it's almost the same, but the other things, there is a spinning required and things like that. Anyway, so what we do in solid state NMR is use a magic angle spinning. Now, that is for this CSA, that is chemical shift anisotropy, and dipolar coupling. Both has anisotropic terms, and that depends on 3 cos square theta minus 1. I will tell you a few in detail. What you require is, in solid state NMR, is put it under a rotor. Okay, this is rotor, not the sample tube that I've shown you yesterday. Okay, we have to have a rotor. A rotor is that it's the actual rotors are like here. Okay, this is €1 coin, and you can see all the rotors. And this is a 4 mm rotor. This is 3.2. This is 2.5, and this is 1.3 millimeter rotor. Outer diameter thickness. Okay, outer diameter. Sorry, 1.3 rotor. It's very, very tiny. It is even difficult to actually see in the thing. So we have to really look for it. And also, what is important is there is a cap. You see this is a cap, and this is the rotor body. We take out the cap and fill the substance, whatever solid substance, very tightly. It cannot be loose. Okay, then it cannot spin. So we have to fill this inside this rotor body with your substances tightly, and then close it with the cap. There is a Bruker video, but I'm not showing it right now. But if you want, I can send you the link that will show how one should do this rotor packing and things like that. Anyway, that is inclined at an angle 54.7, which is called the magic angle. Now, why is it magic? We will come to that. Okay. Now, the orientation dependence, I told you, it depends on a second order. This one, rank 2 tensor. And rank 2 tensor is 3 cos square theta minus 1 dependence. And when does this goes to 0? 3 cos square theta minus 1 goes to 0 if your theta is 54.74 degree. 54.74 degree. This is a magic angle. This is a magic angle. If you keep it in the magic angle, then if it is a single crystal, everything will be unidirectional. Then at 54.74, you will get no dipolar coupling, no CSA. You will get perfect isotropic signal, just like your NMR, just like your solution NMR. Very nice signals. Unfortunately, that is not correct. You mostly work with some crystals, 2D crystals, not 3D crystals. 2D crystals, you will probably work with powder, you probably work with amorphous solids, jelly substance and things like that, where we cannot actually orient every bond to 54.74. So what we need to spin it so that the net angular dependence is still 54.74. The only difference is that we have to spin it at a really high frequency. You have to match the frequency of these interactions, these hydrogen dipole interactions, if you really want to overcome that. Most of the time, we will not be able to do that, and we still see residual dipolar couplings or the residual effect of these dipolar couplings in the spectrum. Anyway, so this is what we need to do. This 3 cos squared minus theta comes from the dipolar interactions, okay? The dipolar interactions and CSA. Okay, and if you keep it to 54, theta being 54.74, then it goes to 0. So these dipolar couplings are going to vanish, and that is why it's called a magic angle spinning, a magic angle. Now, why do you spin it? Because not all bond vectors will be aligned at 54.74. So you have to spin it really very hard. So the net resultant vector will be around 54, will be aligned along 54.74. Now, so we are basically mimicking the tumbling of your molecule. Like the solution NMR, you basically have a lot of tumbling, it averaged out to 0. That is what we are doing by spinning it at 54.74 degree. I hope it's clear. Right, now I'll come to all these interactions, and you see this interaction with magnetic field is around megahertz to a few 100 megahertz, right? So 10 raised to 6 to 10 raised to 9, that is a Zeeman. So you have 500 megahertz, 600 megahertz, 1000, 1.2 gigahertz. All these things comes with the Zeeman interest. That depends on the magnetic field. Okay, it becomes of the magnetic field. Then comes the spin-spin couplings. These are tiny. A proton coupling would maximum go 10-15 hertz, while nitrogen 15 proton coupling is around 90 hertz. Proton carbon 13 coupling is around 140 hertz. Things like that. Okay, you probably have a metal hydrogen coupling. If it exists, then it should be around kilohertz. Okay, so these are maximum, but it's around couple of 200 hertz. I think most of the spin. This is direct coupling, or what we call the scalar coupling. Okay, scalar coupling. That's very small. Compared to come to this dipolar coupling. Dipolar coupling is almost as equal to Zeeman. It's of course less. You don't reach Zeeman effect, but it is less than Zeeman effect. But you will see slowly that what is that. This has a dependence 3 cos squared theta minus 1, 3 cos squared. JJ coupling has no directional dependence. Neither does Zeeman effect has any directional dependence. These two are seen in solution NMR. Okay. Now dipolar couplings has this dependence 3 cos squared theta minus 1. Okay, and what is the interaction strength? It goes from 0 to 10 raised to 5 hertz. That is in kilohertz. Basically, it has in kilohertz. Now, what is quadrupolar interaction on top of that? Chemical shift anisotropy also, it is in kilohertz. Quadrupolar interactions is what is huge. It goes up to 10 raised to 9. This is at the limit of the Zeeman. So this is almost as equal to Zeeman interactions. Quadrupolar interaction is as equal to Zeeman interaction. We will talk about quadrupolar in the later also. Okay, so this is dipolar interactions, and dipolar interaction is this part. You see this part? Now this part has it is between the dipole interaction. You probably have studied dipole interaction in the in your +2 again, dipole couplings and things like that, where you have this term that is mu1 dot mu2 divided by r some power, right? And depending on what it is. Now here, this mu1, mu2, we can replace with this gamma j, gamma I, or some things like that. So you see this part here, not this mu0. That mu0 is not magnetic moment. That is the constant mu0. This is gamma I, gamma. It depends on two. It is between dipolar couplings are between two spins. Okay, each spin. This is of course spin half things. So if each spin is spin half, each spin half is a dipole. Okay, each spin half is a dipole, because that is why you represent like a north-south magnet in your when you are studying NMR. So each spin is a dipole. Okay, you cannot have a monopole. First thing, you cannot have a monopole. So if you are talking about a magnetic moment, if it has a magnetic moment, then it should have a dipole, at least one dipole. Okay, and spin half is the least thing, and that will have a dipole. Now that is a dipole. Then dipole, if it interacts, this spin interacts with the second spin, and this is a dipole interaction. Okay, and dipole interaction depends on the in the denominator you see r, the distance between the two spins, two dipoles, that is r. That is the distance. It's r raised to q 3, r cube, right? R raised to 3. It also have these constant. It can be multiplied. So this plus this plus this plus this plus this. These are the A, B, C, D, E, F. This is the thing. Yeah, that will be here. So these are the things. What basically gives you the strength or the amplitude of this coupling is this distance r and gamma I and gamma j, which basically give you, this will just modulate how it is based on the theta value. Okay, this is a spatial modulation, and this is the actual strength of the coupling, we can call. This is the magnitude, and this is the spatial part. So if you have a proton-proton pair, and if the distance is 10 angstrom, which is pretty large, you still have 120 kilohertz as the coupling, 120 kilohertz. You know our proton-proton vicinal coupling, that is nothing, like 10 hertz compared to 120 kilohertz. So 120,000 hertz, 120,000 hertz is the 1H1H dipolar coupling with 10, which is pretty big. So 1 at 13C, 1 angstrom difference is 30 kilos, 30,000 hertz. Normally 1 is 13C in scalar coupling. You know, the through bond coupling is 140 hertz, and compare that to 30 kilohertz here. Okay, it's huge coupling. So it will couple to everything. You know, if you have a proton, and then there are carbons everywhere, that will couple to all of your carbons in your sample. Not only the same molecule, but it will couple to the next molecule, because it is solid. It is very close to each other, right? So it will couple to the entire. So there is a huge network of coupling. Remember, it's a huge network of coupling that is going to happen, okay, between these things. So you will get a very broad spectrum, couple everywhere. It's going to be very broad spectrum you're going to get. 1H13 with 2 angstrom is 3.8 kilohertz, which is also very high. That is 3,800 hertz. Right, now how does it matter? Just think about two spin that is coupling. Okay, two spin that is coupling. Here, for example, alpha and beta states. If the theta is 90 degree, okay, theta is 90 degree, it will be in this state. Okay, there is maximum coupling, because your cos squared, cos theta, cos 90 is 0. So you will get the maximum coupling like that. Now, cos 90 is 1, so you will get a maximum coupling like that. When theta becomes 60, it will scale down, because when your maximum coupling is when your theta is 90 degree. Remember this? If you put 90 degree here for that particular distances, then this would be the splitting pattern for two spins like that. Okay, one spin which will split into these two peak like here. Okay, now we represent it like this. This is the angle between the two spins. This is one spin, this is a second spin. Okay, and this is lying perpendicular to your B0 field. This angle is 90 degree. Okay, and you will get the maximum coupling. Now when the theta becomes 60, so you see this 60 degree, 60, then the coupling has reduced. When theta becomes 54.74, what happens? There is no coupling. Both of the signal are on top of each other. So there is no coupling. There's no coupling between them. When theta becomes 30, it has gone back. Then when theta becomes 0, actually which is exactly this actually has the highest cos theta. We should check. This has the which is on the other side, which will have the maximum coupling constant that is coming up. Now, when you put all these orientations and you have to integrate, you have to do this 3 cos square theta minus 1 sine theta d theta. You will get that most of your peak, if this orientation is basically determines this orientation, because this is in the XY plane. This will be, so if you have like that, Z. Oops. So this is your X and this is your Y. Your signal, your spins lie in this direction. So this plane, XY plane, there is largest possibility of your sorry, I'm sorry, it doesn't come. Yeah, the largest possibility, the maximum possibility of finding your spin pair in the XY plane is larger. The maximum possibility is having your spins in the XY plane, because there is more space there, right? You know, if you take a sphere, what we are doing here is integrating over the entire sphere. Okay, integrating over the entire sphere of your space. Now, what happens? You find that this, and it is intuitive also, that your spin pairs has largest possibility of being in the equatorial plane. In the equatorial plane, because there is a lot of space there. As it goes down, as it goes further down to make into a sphere, there is less possibilities, right? So in the sphere, it is maximum possibility, and that's why this intensity is high for the 90-degree pulse. That is what I mixed up with higher. This time, when theta becomes 0, we'll have the maximum coupling, but the maximum possibility of finding the signal is along the equatorial plane, and that is why the peak pattern, which is called a peak pattern. This is the standard peak pattern powder spectrum of any molecule under no mass, okay, without any magic angle spinning. We are not doing any magic angle. If you're doing it, this will get narrow. But if you're not doing it, this is what the peak pattern will look like. Okay, so your intensity would be maximum for the 90-degree, because that's where all your spin pairs are supposed to lie. There's a maximum probability of finding it. Similarly, in chemical shift anisotropy also, this is what we have. The only thing is that there is you have the similar angular dependence, and you will get, see again, we have the it is represented like a ellipsoid again. Okay, it is represented like a ellipsoid. So the isotropic, this part is what we actually see in your solution NMR. This is basically the, if you are representing anything in I said second rank tensor, which is basically means a 3x3 matrix, a 3x3 matrix, and you will have in your 3x3 matrix each direction. So each direction will have its own elements. So is it XX, so XX, XY, XZ, YZ, YZ, like that. It goes on. You can convert that into if you diagonalize this matrix, you will get sigma 1, sigma 2, 2, sigma 3, 3, diagonalizing this matrix, and sum of this divided by 3 is the isotropic component. That actually is what we observe in solution NMR. But however, in solid state, we don't see that. We see this. There is a anisotropic part and there is a rhombicity part, and that is what we see here. This is the isotropic, right in the middle, right? When sigma 22 equals sigma 33, this is sigma 22 equals sigma 33. This is the axial symmetry that we are talking about. When sigma 11 is equal to sigma 22, this is the pattern that you're going to get. If all the three are not equal, then because you got a non-axial CSA tensor, it's like this we are getting. Right, so this is what happens. So if you take methane, solid methane, and take which is a spherically symmetric tensor, then that means every direction it is a same chemical shift. Then you get a single peak even in solid state NMR. So if you have a very spherical, a very symmetrical molecule, then it is easy to get a well, you will have to have dipolar. You will have dipolar couplings, but we can eliminate that through CSA, spinning at magic angle. But other than that, you will get a single peak. If you eliminate the dipolar coupling, you will get a single peak, and which will be very nice. If non-axial symmetry, that is shielding is different in 3 directions, then you will get, because your sigma 11, sigma 22, and sigma 33 are different. Sigma 11, sigma 22, and sigma 33 are different. You will get a peak like that. This is for ethylene molecule, and you will get a peak like that. But if it is axially symmetric, one axis it is same, then you will get a peak like this. Okay, so from the CSA, you should be able to figure out also the shape of the molecule. So analyzing CSA would give you actually a good idea about the shape, but the analysis itself is going to be a little more complicated than what we are used to in solution NMR. Now, as I told you in NMR, that what we have is that is you wanted to eliminate dipolar couplings. Now, one way of eliminating the dipolar coupling would of course be is to make this gamma smaller, right? Make this gammas smaller. So if this RDD is reduced, how can you reduce RDD? The magnitude of the dipolar coupling. How can you reduce it? Measure at a lower gyromagnetic ratio. Okay, in protons, what we need, we would like to have at a higher gyromagnetic ratio because your sensitivity is higher. It is actually true. In solid state also, we should hope to measure at a higher gyromagnetic ratio for the sensitivity. But then your sensitivity is basically killed by your dipolar coupling because it gets split. Your protons are getting split left, right, center because of the dipolar coupling. So what we have to do? We rather don't worry about the sensitivity that is gained by the proton by measuring on a proton. Rather than we want to reduce the complexity of the spectra or reduce even because of the splitting, it is already too broad. Okay, so we would like to measure at a lower gyromagnetic ratio. So you can either measure at carbon 13 or you can measure at 59. Carbon 59, of course, is much lower in sensitivity due to lower gyromagnetic ratio as well as lower abundance. Carbon 13, on the other hand, is 1% abundant, and gyromagnetic ratio is only 4 times less. Okay, so you rather measure on carbon rather than protons. Now, the other problem is that, of course, if you're measuring on carbons, then your sensitivity is lost because, as I told you, you are reducing the gyromagnetic ratio. You hope to measure on a high gyromagnetic ratio, right? So you have a problem. So how do we recover? How do we actually increase the sensitivity of carbon? That is through protons. Now, in solution NMR, we have something similar. It's called the INEPT or DEPT, if you know. INEPT is insensitive nuclei enhanced by polarization transfer, where you transfer the magnetization of the hydrogen or proton to the carbon through J coupling. The scalar coupling. Now, in cross polarization, we cannot do INEPT here because the J coupling is only in hertz, few hertz. It will have to stay on that your magnetization has to be on the transverse plane for a pretty long time before it can be transferred to carbon. Okay, that is not acceptable because if you, as soon as you put a 90-degree pulse on a proton, very soon, in few milliseconds, not in few milliseconds, actually few microseconds, maybe up to 1 millisecond it will survive, depending on the symmetry of your sample, and then it's lost. It's lost. The T2 will kill it. Okay, so you cannot do this J coupling based transfer to the proton to the carbon insensitive nuclei. Here, the insensitive nuclei is carbon 13. That is not possible. Now, how do we now get out of it? How to do it? We use dipolar coupling. We use dipolar coupling for the transfer to happen. Now, we cannot use INEPT. That is not possible because that is a different technique. The coupling is not so extensive, so we know exactly where the spins will end up. That is not possible. How do we do that in solid state NMR? That is through what is called spin locking. Okay, it's called spin locking. So you do a proton 90-degree pulse. You keep all your magnetization of the proton into the XY plane and do what is called a high power spin lock. Okay, you put a very long ping, not very long, is somewhere around 100 microseconds to 1 millisecond. 1 millisecond spin lock, 100 microseconds to 1 millisecond spin lock. Simultaneously, you also have the spin lock on the carbon-13. Now, how is that? The B1 on the carbon, gamma B1 of the proton should be equal to gamma B1 of the carbon-13. Okay, you have to match this. What are we doing here? Basically, your Zeeman interaction, Zeeman coupling on a lab frame. This is very high because that is it's in let's say it's 400 megahertz, and this is 100 megahertz. Okay, but so it is not possible to transfer a magnetization from 400. This difference cannot be compensated from and transfer it to this because it's too big. You see, that is why, in our society also there is government. The government tax the rich, right? Government has different slabs of taxing people. Okay, you cannot tax. We cannot tax the poor people the same amount like the rich ones, right? So we can't do that. And there is no way the rich is going to give it to the poor without the government pressurizing them, right? I hope I'm not a communist by saying that. So the rich will not give you the proton will not give it to the carbon-13. This is okay. So what we'll have to do, we have to match them. We have to put them into a different universe where they have the same splitting. They have the same splitting here. This is possible by doing this. What we are doing basically is to quantize it along the RF field. Previously, it was quantized along B0 field. Now we are quantizing it along B1 field. So now we are basically quantizing along the RF field such that their splitting has now become equal. Now proton should not. Now he is my brother, so proton will see that he is my brother. I have to give some money. Previously, I don't know, this guy kind of attitude would be for the proton and carbon-13. Okay, so that was not possible without doing this matching business. If it's not for the matching, we will not be able to transfer magnetization from the proton to carbon. So this thing is called a Hartmann hand match. Hartmann hand matching or hand matching. Unfortunately, he did not get Nobel Prize. Hartmann hand. So this matching led to this. We can easily transfer magnetization from proton to carbon, and then you acquire on the carbon-13. Now what happens? The carbon gains the sensitivity of the protons. Okay, so that way we compensate for the less sensitivity of carbon by transferring magnetization from the proton to carbon. That is the takeaway. Okay, we compensate the magnetization loss by acquisition on carbon-13 by transferring the magnetization from proton to carbon. All right, let's see how magic angle helps. Magic angle can then increase the sensitivity. So this is for a tin 119 spectra. If it is in a static spectrum, you will see such broad peak. Now you go spin at 3 kilohertz. 3 kilohertz, you see these sidebands. Now the sensitivity is being lost to these sidebands also. So what you have to do is, because it depends on the strength of the CSA that is there. Now you go spin further high, that is 5 kilohertz. Now the sidebands have reduced the sensitivity of the central line. This ISO1. This is the isotropic chemical shift. That isotropic chemical shift is increasing. See this isotropic. This is you take this thing. It will not be isotropic. You see, this is the isotropic. Exactly, this would be a isotropic chemical shift, and that is possible if you spin higher. Now, if you spin further, 5 kilohertz is very small actually. You can spin to 10, 20 kilohertz. Then you will not see any sidebands. You will see a single peak, and you should be able to see. This is, of course, tin. It's a tin spectrum, NMR spectrum. Right. So how are we going to do that? Now, how are we going to do 2D NMR and things like that? That is possible also. So what we have to do is we have this broad line, that is a static sample. We put it in a mass rotor, put it at a magic angle and start spinning. Then you will get a narrow lines, carbon of course, but still narrow lines. Now the problem is now we have to do correlations like COSI, NMR and things like that. But we don't do COSI, but still something very similar. We have to do it in 2D. But then we lost all the interactions, right? So how are we going to do that? We have to reintroduce. We have to reintroduce this coupling. We have to reintroduce this coupling. It's called recoupling. Professor Madhu is very famous for this recoupling and decoupling sequences. So he should have been the one who should be telling you this. So you have to recouple the coupling. You lost the coupling when you do this mass NMR and decoupling sequence to get this very narrow spectrum. But then you will only get these diagonal peaks. You will get only the diagonal peaks. Now you don't want that. Only diagonal peaks is not useful, right? If you want to see a correlation between these two, you need to transfer magnetization like that. Okay, you get a COSI kind of spectrum, right? COSI kind of spectrum. Then you see that this guy and this guy, this guy and this guy are coupled to each other. Otherwise, it's useless. You got a diagonal peak. That is not useful, right? So if you want to see this guy is coupled to this guy, or this is close to each other, then we need to couple them together. So what we do, we need to reintroduce coupling, either through J or D decoupling. So what we call recoupling, we have to do a recoupling sequences in order to do that. Okay, so there is a whole bunch of sequences and still modifications are going on the recoupling sequences in order to do that. We can also do higher 3D NMR and things like that in samples that is quite conducive. So here again, it's a combination of different CP. In solution NMR, probably in the mornings, she might have told you about how you do 3D NMRs, right? And how we can get structural information from it. How we can assign molecules, especially protein molecules, where we do multiple multiple magnetization transfer. So you have proton to carbon-13 to 15N, like that transfer. Okay, that was possible in solution NMR. In solution NMR, it is also possible, and we do that in solution NMR using insensitive nuclei. Insensitive nuclei enhanced by polarization, right? Inept building blocks, we call it building blocks. Inept magnetization transfer, building blocks, we use it to transfer magnetization between proton, carbon-13 and 15N. But now we replace this inept, in solid state, we replace this inept with CP, cross polarization. Okay, so again, the Hartmann matching between the 1H and 15N. So you have to make the RF fields of one or RF strength of 1H and 15N together the same, so that there is a magnetization transfer from proton to 15N. Then we allow it to evolve. Then we do a transfer from 15N to carbon-13, again matching all the chemical shifts. Then we detect on carbon. So you can transfer like that. 1H to carbon-13 to 15N, and you can get spectra like I'll show you the spectra. I'm sorry, this is just even with all this, we will not be able to. Oops, this is going on. Yeah, you get this kind of spectrum, this NCOCX. That means I have transferred magnetization from 1H to nitrogen, then to CO, then to the C alpha and C betas of the protein. This is protein samples. Okay, so I go from 1H. Sorry, let me put. So I go from here. So I go from H, all these H's. All these H's, I transfer to nitrogen. Now and then I transfer to this CO, because this is the closest CO. I will not be able to transfer to this CO. So I go to this CO. Then I transfer to C alphas and C betas of this. C betas. Okay. So this is possible. There is also NCA access. So I go this way. NCA, proton to H, to C alpha, then C beta, and things like that. Then the same HNCA. This is like an HNCA. This is HNCA. If you're probably the lecture in the morning should have given you this. This is like an HNCO. Okay, and this would be this is same. This is an HNCA and this is an HNCO. Okay, from the morning thing. Then you will be able to do assignments like that. This is what we do in our solid state NMR. We can also find distances. We should be able to find distances also. So we should be, what we do is called a CHHC experiment. CHHC experiment, where we transfer magnetization from the hydrogen to 13C, then put it back on hydrogen and do kind of a no-C mixing time. Again, each of this peak here, if there is a cross peak there, that means that they are close to each other by within the distance of 6 angstrom. It's not 5 angstrom, it is 6 angstrom. That's all. One can do very fast mass. I showed you this 1.3 mm rotor, right? 1.3 mm rotor can go to a spinning speed of around 70 kilohertz. Okay, it goes up to 70 kilohertz mass rate. Okay, mass 70 kilohertz, really very fast. Okay, and however, your CP, I told you Hartmann hand matching. Hartmann hand matching will not work so very well. So you have to have other types of magnetic transfer. So it is possible to do it with low pass, low power magnetization transfer. And it is again, we can do all this NCA, NCOCX, and CC, NCA, HNCA, HNCO, and COSI type experiments in solid state. And we'll be able to find out this one. Again, Professor Madhu also worked extensively on the decoupling and recoupling part of it, not the actual magnetization transfer. This is our work that we did. And we also can do, this is at 60 kilohertz of mass at 800 megahertz. You can see, you can also walk through the resonances and easily identify many of these for ubiquitin, which is the standard protein. And we should get very nice peaks like here. Very nice, looks like solution NMR. Right. Only thing is these are 2Ds. That is the only difference that we have to do. So we have, but still we should be able to get almost all assignments from at least for small molecules. It is possible to do that. Right. So now comes the idea of quadrupolar nuclei, and with this I will end after some maybe 5-6 minutes. So quadrupolar nuclei. The problem with quadrupolar nuclei is that the nuclear charge distribution is not uniform. In your spin half molecule, the nucleus is spherical. That means it is uniform. The charge distribution is very uniform. Okay, the nucleus is spherical. Okay, when you represent your nucleus in any of your drawings, most of the time you represent it like a sphere. But that is only true for spin half nuclei. Okay, if it is a quadrupolar nuclei, anything which the spin greater than half, then it is no more spherical. It is elongated, or it's not isotropic. That's a basic thing. You will have multiple charges and multiple poles. So you will have all kinds of other interactions that is possible. Just like your chemical shift anisotropy, it will have this 3x3 matrix. Now, unlike chemical shift anisotropy, you don't have an isotropic component. So in solution, you don't see it. You don't see the sigma 1, V11 plus V22 plus V33 divided by 3 thing. That is not good. That is not there. It is actually, it is traceless. That means V11 plus V22 plus V33 is actually 0. So, yeah, V11 plus V22 plus V33 is actually going to be 0. So when in solution, this quadrupolar interaction actually vanishes. But in solid, this will be present, and that will be a huge problem. Now, huge problem is that it is not only the problem is because there are two types of the first order interaction, and there is a second order interaction. Now, first order interaction has this nice 3 cos square theta minus 1. So you put it to magic angle, it should be very good. Now you can spin it, these interactions will go, this splitting and everything will disappear, or this pattern will disappear, just like your CSA has gone, or it has gone into the sidebands. But the problem is the second order interaction. That second order interaction is not 3 cos square theta minus 1, it also has a 9 cos square theta minus 1. That will not go at 54.75. I'll show you the thing. So you see that this is 2 quadrupolar. There is a 0 second and 4th order Legendre polynomial. 4th order Legendre polynomial. This is the second order Legendre polynomial, and this is the 4th order Legendre polynomial. When I say second order Legendre polynomial, this 3 cos square theta minus 1 is always, you probably, even in +2, you should have studied. This is the p orbital. Dz squared orbital. Dz squared orbital. Dz squared orbital. Dz squared orbital in your of hydrogen atom. Okay, dz squared. So this 3 cos square theta minus 1. But here, for example, it is not only the second order Legendre polynomial, but also the 4th order Legendre polynomial that is there. Yeah? So you have 2 types of angles that has to be. You can see that P2 cos theta, this P2 cos theta drops to 0 at 54.7. 54.3. But this P4 cos theta, they drop to 0 at around 30 degrees. Also, it can go to 0 at 70 degrees. But they don't go to 0 at 54. It is minus 0.5 or something like that. They will be only scaled down, not disappeared. Okay, so you cannot spin at magic angle and expect that the quadrupolar interaction disappears. That is never going to happen. That is not going to happen. What you have to do, of course, is to if you have the ability, that is, if your probe is able to do it, you have to do something called, you have to jump from 37.88 and 79.19, or put it on one of these angles, 37.88 or 79.11. I would rather put it on the 79.19, because there you basically average out the second order interaction. Also, this 4th order interaction, but also it will reduce the second order interaction, which is very small here, right? So that is possible to do it. Okay, so that is one method of working with a quadrupolar nuclei. But we can MQ mass. This is multiple quantum magnetic magic angle spinning. You still keep it at your 54.7 and creates a triple quantum. You can create multiple quantum because of the couplings, and we should be able to do that triple quantum. And this triple quantum actually, that second order quadrupolar coupling is average. Hence, since we cannot directly, that means the second order, this P2 cos theta. This P2 cos theta will be average. So you keep your angle at some 70.12 or something like that. So you should be able to get a very good spectrum. Only thing is, triple quantum, always NMR cannot determine any other quantum other than the first quantum. That is a single quantum. So you have to convert this into the single quantum coherence before actual direction. So you have to go using pulse sequences. You have to create that triple quantum or 5 quantum, 5th 5 quantum, whatever is possible, because there are so many coupling. It's possible to do that. Evolve it. That means there is no second order P2 cos theta interactions. You are speeding at 70 point something, and then just before detection, you go into a single quantum coherence by pulsing, and then you can detect it. Then you will get a reasonably good spectrum. These are some of the, I don't know how much of time is left. I was really fast, is it? Anyway, some example I can give you. So here is, because these are something that many of you might be interested in. That is why I picked up these in examples. Surface chemistry of, there are of course lots of things that one can do with solid state NMR. As I told you, gels, I mean even organic molecules in polymers, gels and organic molecules. If it is not soluble in any solvent, then you probably would like to find something, find some information, then you can do solid state NMR. But what is also important, that surface material science, very lot of applications there in material science, that is important. For example, here this is a example of lithium NMR, mass NMR, lithium mass NMR. and of a electrolyte or electrode material, lithium, manganese, oxygen thing, electrodes at different state of charge. That means you have 0 charge, you have 500 charge, 1000 charge. This one 0, 9, 23, 37, 46, 55, 64, 83. So different percentage of charges. We are looking at this lithium NMR. This is the ppm value of lithium. Okay, and you see that how lithium is moving at different percentage of charges. Now you expect in your electron, this is for a lithium diffusion, an important criteria for achieving high rates and high power batteries. In power batteries that they are working on, this is a work from Professor Gray's lab in UK. So she is famous for doing these fuel cell lithium measurements, where she uses the actual fuel cells in the of the battery and measure these lithium diffusion and things like that. So what does it shows? It shows basically that at different point of the charge, you expect basically all your lithium, the electrodes should not change. That means electrodes change, right? So, but that is not what is being observed. What is being observed, however, is that it is here at first, but as the charging increases, that means you put in a lot of current now on the fuel cell, and now it reaches 83, it has moved. It has moved into a higher magnetic, higher ppm value. That means there is a deshielding happening. Okay, there is a deshielding happening, right? So you see that there is a lot of, it has been converted. It's basically converted to lithium MnO3 compared to these things. So your electrode material is being slowly decomposing. It's slowly decomposing as charging happens. So what is the criteria? What is information that you're going to get out of it? This battery material will not succeed for longer unless you actually change it. I'll change the composition. Right, so you can actually measure all of these things and find out how they are. Of course, we have to. Not all the solid state NMR can do this, but for example, doing in vivo, or meaning right inside a battery cell, right inside a battery cell is not that trivial. That not that easy. Now coming to the surface chemistry of indium phosphate quantum dots. You probably know what quantum dots are, right? Now quantum dots are this materials which semiconductor materials which has a very good optical and physical properties, which it fluoresces. It has a very good optical properties. And it is obviously found in Samsung LEDs, LED TVs, right? Powered by quantum dot TVs. So this is for a surface chemistry of indium phosphate quantum dots, and you see that there are two types of signal for phosphorus. 31p NMR. You just solid state 31p NMR. You see that this phosphorus is for a phosphorus which is attached to 4 indium. Yeah? Now, where do you actually think this comes from? This is coming from the inside. A quantum dot would be like this. Okay. It's a spherical semiconductor, very small in nanometer. Okay, probably 3 to 10 nanometer. Okay, and you will have this phosphorus. There is also phosphorus inside. Now we will be able to figure out which phosphorus is what. This phosphorus, this signal that comes, that should be from the inside, because it has so much of indium inside. It's all converted. All of it is indium. That first of all, when you measure this quantum, there are 2 of them. There are actually 3 of them, 3 or 4 of them. But you see, the major part is the indium, the phosphorus with all indiums in, or bonded to it. Then there is a phosphorus which only oxygens bonded to it. Okay. Then only 1 indium and with 3 oxygen, and this is a phosphate group, and this is 1 indium with a 2 oxygen attached to it. So you see all these 3 possible methods. Now, another important thing is that thing which is useful or have studied is cadmium selenide quantum dot, and this is done through DNP, dynamic nuclear polarization, where we use the sensitivity of the electrons, paramagnetic electrons is introduced as a radical, and then that sensitivity of the electron has been passed over to the for the cadmium or selenium here. So what is interesting is that you see there are this is the cadmium selenium quantum dot. You can clearly see which is the cadmium thing and which is the cadmium core and which is the cadmium surface. Cadmium core is highly isotropic because it is a layered higher order structure. So let's higher order structure. If the cadmium is there, it will have cadmium all over the place, or it is well ordered. So you don't expect so much of anisotropy. That means the peak of cadmium core, that the peak that comes out of cadmium, the cadmium in the core of the quantum dot will not have sidebands. The sidebands are because of anisotropy, chemical shift anisotropy. That means they are not, there is not isotropic, but there is difference in their environment at different directions. So if it is a cadmium coming from the core, it has the same environment all over the place. So there is no sidebands. If there were sideband, there should be a sideband here, sideband there, sideband here, and sideband there, which is not possible. You don't see it. So this is cadmium core. While cadmium on a surface here, for example, a cadmium, if it is there, here there is no cadmium, but inside there will be cadmium, right? So that means there is anisotropy, and that anisotropy will be existing like a sideband that comes out of the cadmium NMR, solid state NMR. You see that, right? In the selenium also, you should be able to. Selenium cannot. One good thing is that selenium does not have so much sidebands, and you can see that selenium is single. That means selenium is not found in the. What does it mean? It means that selenium is not found in the peripheral. In the edges of the quantum dot, it is found inside the core. It's mostly found inside the core. So cadmium is found both inside and quantum dot, not outside, meaning on the surface of the quantum dot, while selenium is found mainly inside the quantum dot. You cannot get this information from any other spectrum, any other. XPS can give you some information, but then it is going to etch out. How do it do that? It etches out the surfaces, and so you're basically destroying the samples, and that is basically destroying you're basically probing it with the very high energy substances. So that will itself interchange the structure of the molecule. Here we can clearly see which substance. In the cadmium selenium quantum dot, cadmium can be found both inside and on the surface, while selenium, for example, can be only found inside the quantum dot, not on the surface of the quantum dot. These things shows you how much sensitivity one gains by doing this DNP. Now this is with DNP. So DNP means dynamic nuclear polarization, where we transfer the electron magnetization, a paramagnetic, that means an unpaired electron has to be introduced, and that magnetization of that electron, here the gyromagnetic ratio of electron is 10,000 times, 10k times higher than protons. So there is a huge magnetization that is there, and that is possible to transfer from electron to either cadmium, selenium, or carbon or hydrogen, whatever is possible, and that is called DNP, dynamic nuclear polarization. And so you see that when you don't have the microwave, that means if you want to excite electrons in order to transfer it, you need microwave radiations, not radio frequency, because it is high gyromagnetic ratio, so it will go into gigahertz. So that is where microwaves are. So you have to switch on the microwave radiation, and then it is possible to transfer magnetization to the cadmium, and you see the increase in intensity. This is when there is no off, and this is when you have on. Good. You can also see this. You can also see that it is possible to transfer. This is a CP. This is a 2D NMR where you have carbon 13 and 11. So carbon 13 in the direct dimension and cadmium in the indirect dimension. So we basically looking at correlation between carbon 13 and cadmium. So what is that? Cadmium is capped, or cadmium selenium content dot is capped with this organic molecule. So if you see a correlation between carbon and the core, then that means that there is a transfer of magnetization from carbon to the cadmium. You see the surface. Sorry. You see that this surface quantum dot, this minus 400, minus 200 to, I think minus 200 to 400, right? Minus 200 to 400, this guy, surface, minus 200 to 400, this guy is having a higher intensity because there is a lot of transfer between this carbon and this one, while this, the core one is basically nothing. There is absolutely nothing. What are these then? These are, the core should be here, around 0 ppm. You can see it here, around 0 ppm. That is missing. There is no correlation here. That means there is no, that is a core cadmium. While the surface cadmium, there will be always correlation. So what are these peaks here? These are the side bands, as I told you, because if it's on the side, it's on the surface, that means there is a lot of anisotropy, and there will be side bands that is present. Okay. You can also combine protein and quantum dots, and this is an experiment that we have done with these dots are protein signals, and the green and the red, the black ones are the solid state NMR of the protein conjugated to the quantum dot. And we found that many of this area here, you can see this area does not have these black things, which will tell you that there is a problem, that when protein has conjugated to the quantum dot, the protein structure has considerably changed. At least some part of the structure has changed. Okay, thank you, guys. If there are any questions, you can ask.
Yeah, thank you very much for this wonderful talk. So this is the time for discussion. So there are some questions. May I read it? How do you find out the structure of covalently modified graphene?
How do you find the structure of covalently modified graphene?
Yeah.
The structure is a big question. So what are the modifications? Yes, you can be able to figure out. But then first you do IR and other stuff before you know what kind of functionalization that you have done there. If you know all the functionalization, then we will be able to figure out at least where where at least it is being changed and things like that. But I do not know what the modifications exactly you mean. There will be, of course, a chemical shift change. If graphene, for example, if you get a single peak, okay, and then if there is a modification, then they will get there will be more peaks. And depending on where shielding or deshielding, we should be able to see what kind of modification are they. That is clear. So just looking at the chemical shift, it is possible to say that there is modification or not. There is no modification. That is clearly possible.
Okay, thank you. So there is one more question. Can the amount of cadmium inside the quantum dot be known exactly?
Exactly. See, NMR is not an exact method in determining the concentration and things like that. And if you have a standard, then you possibly can do it. But otherwise, you have to have a calibration curve first. I don't think that is possible with cadmium. So anyway, in our see, for example, our integration of a small molecule in NMR will tell you just that there is proton, how much of proton in it. It doesn't tell you how much amount of proton in it. You know, see, it's a different thing. So say I have 2 molar of H2O. I put 4 molar of H2O in the same NMR tube, it will give you the integration as 2 because you are doing it. Let's say you have CS3OH. Okay, CS3Cl. No, wait, CH3, CH2Cl. Okay, CH3Cl. You have 1 molar, 2 molar, 5 molar. It will be same, 3:2. The integration will give you 3:2. Right? It will only give 3:2. That is just a representative of how much that is that integral. Solid state NMR on the other side even cannot integrate also. That is also possible. You cannot integrate like that also. Okay. So that is also possible. We only in any NMR absolute concentration is not possible unless you make a what is that called a calibration curve. Now we know exactly for 1 molar I get this intensity. Now for 2 molar I would expect something else. Then I can actually know the concentration. But then you have to know it earlier. What was the concentration, not from NMR. Okay, because it's an insensitive method. You can't. It's not like UV. The reason is that all the nuclei are not in the ground state. It is equally populated. The up and the down state are equally populated. So UV, for example, all your molecules are in the lower energy state. So the absorption directly equals to the concentration. Okay, NMR that is not the case.
Thank you. So one more simple question is there. In quantum dots, small peaks are there. Is it noise?
Yeah. Which quantum? Where you're talking about these things? Yeah, these are noise. It's very. I told you this is an example of how DNP is used to enhance the sensitivity of a cadmium selenium quantum dot. So the active nuclei is very small inside a NMR tube. You saw NMR rotor, right? NMR rotor. So you will get you can't expect the level of noise like in solution NMR. Solution NMR, you will get a very flat line like that. But that is not possible in solid state NMR. You will get wiggling like that. These are noises. But these peaks, you see, these are not noise. Clearly not noise. Okay. This is not noise. Comes out of it, it is not noise. And these line widths are pretty huge. It's not 1 hertz or something. This will be in kilohertz, or even hundreds of hertz. Okay. So that is why I told you that the interpretation is not that straightforward in solid state NMR. You cannot expect the level of sensitivity that you expect, also the resolution that you expect.
Thank you.
But you get a lot more information. If you will get the shape of the molecule. If you analyze the CSA tensor, you will get information about the distances, angles. All of this is possible with solid state NMR. That is not really possible with solution NMR.
Thank you. Is there any question? Some more questions are there?
What is important is you should do solid state NMR when everything else fails. And that would be the most because the analysis is not that straightforward. Unless you really want to know a very specific thing, you wouldn't be doing solid state NMR. That is what I want to tell you. You shouldn't be doing solid state NMR unless you want to know very specific state, a specific thing, or something that is not possible to do with any other spectroscope. You will be able to get a lot of information, but then you should ask the right questions. That is what the important things.
Thank you.
Coupling constant useful in solid state NMR. Coupling constant is if you are talking about J coupling is hardly used in solid state NMR. The J coupling is, and I told you, the strength of the J coupling is only hertz, 10 hertz, 20 hertz, like that. while we are dealing with kilohertz in dipolar coupling as well as CSA, megahertz for quadrupolar interactions. So these coupling constants are nothing. I mean, the scalar coupling is nothing compared to the other couplings that is there in solid state NMR. So basically, coupling constants are eliminated, or it's negligible, okay, compared to the strength of other coupling constants. So we don't worry about J coupling so much, unless you actually spin it to really very high, like 120 kilohertz, 70 kilohertz, and things like that. Then we have to worry about coupling constant also, because then the lines have become very narrow, and then coupling constant is also a problem that will broaden the spectrum. So you should be worried about that also. But until we don't reach those much spinning mass frequencies, then we don't have to worry so much.
So thank you very much. Is there any question?
If there are any further questions, you can also write to me. I'm very happy to, from yesterday's talk also. I think there is no more.
Yeah, Dr. Vinesh, thank you very much for the two very informative talks about NMR instrumentation and the solid state NMR. So thank you very much. Thank you.
Thank you.
Thank you, Dr. Vinesh.
Thank you very much.
Thank you.
Can I log out now?
Yes, we can log out.
Thank you very much. Bye guys.
Thank you.